Next slide. Okay. It's a pleasure to have Gabriela Sato-Polito today. Gabi is a postdoc at the IIS. And before that, she did her PhD at Johns Hopkins with Mark Microscopy. She works on a variety of topics, including dark matter, action dark matter, intensity mapping. But today she will tell us about pulsar timing arrays and the nano-hertz nano-hertz background from supermassive black hole binaries. And I'm sure you give some introduction, but this was a big deal that there was a claim detection by PTAs. And Gabi showed that the background is significantly higher than what you expect from other concentrations. So, go ahead.
Thank you. We can close that door and maybe get them to close their door.
Yeah, thanks for the introduction. Yeah, I'll talk about pulsar timing arrays. This one's just working. It's like,
Okay, yeah.
well,
There you go.
okay,
Okay.
cool. Sorry. Yeah, so the basic idea behind pulsar timing arrays, right, is that we can observe pulsars in the galaxy. These are neutron stars with beams that rotate. And every time this beam crosses your line of sight, you see a little blip. And this kind of amazing stability of these pulsars allows you to think of these as very stable clocks. The idea is to try to look for these pulsars that are spread out across the galaxy. The stability, just to give a little example of what it means to have an amazing stability for these clocks. These are just some kind of somewhat historical papers, but from this annual frequency control symposium from '87, saying basically that millisecond pulsars rival the best atomic clock stability. This paper here on the right is looking at using pulsars for an X-ray emission from pulsars specifically for navigation systems in space. And this is comparing some stability of pulsars with atomic clocks over various timescales and showing that these are indeed very stable. So this is what it means to have a very stable clock.
So how could they measure that the pulsar is more stable than the best clocks?
Good question. I'd have to look at this.
Maybe they used a bunch of clocks.
Well, they definitely
There's an error bar on both sides.
Yeah.
they definitely compare different like atomic clocks for their comparisons. But yeah, I have to look at this paper.
Maybe it's the same question, but a slightly more relevant question is not exactly the uncertainty, but whether or not you can phase it. So meaning you know how many ticks it was from 1987 to the present. See what I'm asking? It's a slightly different, it's very related to timing error, but it's not quite the same thing.
Well, this is probably looking at like just the variance. You have, given your understanding of the ticks of your clock, and this is the same thing as pulsars, right? But you would expect your next tick to arrive at a certain time, but then there's some variance in when this tick arrives. And
I guess
this is
I'm asking, do you know how many decades out you can predict the ticks?
I mean, this is what this time scale here is, right? It's the stability of your ticks over that time scale.
Right, but if 10 to the minus 13.
I mean,
It's
this
sigma.
quantity is, yeah, it's
It's a detailed question whether that is sufficient to predict actually when the next tick will
I
arrive.
think they're sure that they haven't missed a tick, if that's what you're asking.
Yeah, that's what I'm asking, is
Yeah.
whether a tick's been dropped since 1987.
No, I don't think so. And I do want to note that atomic clocks have since improved quite
For
a bit
sure,
by
for
5
sure.
orders of magnitude.
yes. Well, this paper is actually from I think 2008 or so.
Okay.
These are not the same papers.
Yeah.
But yeah, I mean, both have improved. Atomic clocks have improved a lot. But yeah, the main point here is just that they are comparable. And atomic clocks errors are actually something that PTAs have to care about. So the sort of general idea, right, is then if you have this very stable clock, is that you can use this to try to measure deviations from those ticks. from gravitational waves. And the sort of order of magnitude for how precise this needs to be is basically set by what your target sensitivity should be, so what strain you're trying to measure. So this is basically measuring these deviations in time over your total observing time. If you want to measure some astrophysical object, which we'll get to later in this talk, your target is something like 10 to the minus 15. You're observing this over the scale of a decade. You need a timing stability of around 100 nanoseconds, which is achieved currently in arrays. So this is more or less what you require to measure gravitational, to plausibly detect gravitational waves that we expect to see. Now, to be a little bit more specific, you can define this timing residual, which is the relative shift in the period of your pulsar. And you can show that this is given by the difference between the metric perturbation on Earth. So here the direction of the pulsar is p hat a, and you have a gravitational wave, say, traveling in this omega hat direction. The shift in your pulse, this relative shift, will be given by this difference between the metric perturbation on Earth and at the pulsar, and then projected along this Earth pulsar axis. The regime that we expect PTAs to be in is essentially this stochastic regime. So essentially, you can think of this metric perturbation as a random field. And so I can take the timing residual that I had defined before, and in this regime, you're really just measuring the superposition of all of the gravitational waves coming from every direction, omega hat here. So you're integrating over omega hat. I've written this as a Fourier expansion, so here is a function of frequency. And this difference between the Earth and the pulsar become this phase difference that we observe. And I've also grouped all of these geometric factors into this quantity f, where capital A here is a sum over all of your, over both of your degrees of freedom. So this FA is usually called this antenna beam pattern. It's basically telling you how your timing residual for a given pulsar responds to a gravitational wave coming from direction omega hat. And it's basically just this geometric quantity that is just dependent on this on these angles and on GR, basically through the allowed degrees of freedom that you have.
There, tau A is the time distance to the pulsar.
Yeah.
And you're assuming, but this is slightly odd because are you assuming that you know the positions of the distances of the pulsars?
No. So ultimately, you'll think about this as a statistical quantity, and so here
you'll
is a
treat
random
the thing in
phase.
brackets as being a half.
Yeah, and so this basically is treated as just a random phase. So the idea is then to treat this your metric perturbation as some stochastic field, because it's a superposition of waves. The mean is 0, and the first non-trivial thing that you can consider is the variance. And if you compute the 2-point correlation between your timing residual, so here I now have two pulsars, one at a direction p hat A and p hat B. This correlation will be determined by the variance of your gravitational wave field. So taking the expression that I had before and making a few assumptions, you can show that this correlation is basically given by an angular component and by an overall amplitude that is telling you something about what produces your sources, about the gravitational wave energy density, basically. And this angular component is known as the Helly's and Downs curve. It's just this integral over gravitational waves from all directions, in particular these geometric factors that I had mentioned before. And so you've probably seen this curve before. This is what this curve here looks like. This angle is just the angle between your two pulsars, and this is telling you what the correlation between pulsars separated by this angle is. So it has its maximum value when you're looking at two pulsars that are coming from the same direction. And again, remember that you're integrating over the entire sky in gravitational waves. So if they're in the same direction, when you do this, basically both of your pulsars, you're observing pulses that are either traveling, with the gravitational wave or against it in the opposite direction at the same time. This correlation decreases as you increase this angle, and when you get to, opposite directions, they're, either going with or against the gravitational wave in opposite ways. And so this doesn't quite get back to the initial correlation that you had, but so this is basically what your Helings and Downs curve is telling us how,
This integral over frequency.
Yeah.
What is? Wait, what does that integrates over all the frequencies? Okay.
Yeah.
Is there anything interesting about it being the minimum not being quite at 90 degrees?
It's just a consequence of this fact that if you have two pulsars in the same direction versus at slightly different directions compared to the gravitational wave direction that you have, you don't really get the same results. And so this slightly shifts the shape of this curve and introduces this, both the shift of the minima and the fact that it doesn't go back to the 180.
And
Yeah.
this is assuming basically that there's a continuous spectrum of gravitational waves and there's not like a small number of really big ones.
Yeah, we'll get to this question in the second half of the talk. We'll talk about what happens when you have when you do have these basically Poisson fluctuations in the number of sources. Yeah. And,
I am wondering about the low frequency cutoff of this integral. Does it matter? Like, does it have because I mean, obviously, if you did like 6 months of observations, there'd be some relevant
yeah.
cutoff. Like,
Yeah.
How does that work?
So in practice, I mean, here this is shown in the time domain, and you basically in practice there's always a minimum frequency that you can access, which is the inverse of the observing time. And so, yeah, in practice you do have this cutoff, and it slightly changes this.
But I mean, I guess I'm asking, does it matter? Like,
You can
in
easily-
terms of the this is a prediction.
Yeah.
And do you
it's just-
expect those frequencies to matter if you've observed for 14 years or?
I mean, I guess the point is that you just adjust your prediction, right? You're
Okay.
I mean, this
You
is
just
showing
know
it
how to
conti-
do it.
Yeah,
Okay.
you're just showing this as like you're a continuous Fourier transform, but in practice, you have some like discrete, you have some discrete sampling in time and some maximum time. So this is a discrete expression,
Okay.
but you know how to
You
compute
just-
that. Yeah.
Okay, you just do it self-consistently.
Yeah.
Yeah, okay.
Cool. Oh, right, yeah, so the basic point here is that this Helings and Downs is just a geometric quantity that you computed, and it's basically telling you that what you're seeing, the correlations between the shifts in arrival time of pulses is produced by gravitational waves, versus this amplitude is telling you something about the nature of the sources that you're measuring, what their energy density is. And so this kind of first evidence for gravitational waves was announced in 2023 by multiple PTA collaborations, and these two components that I just mentioned were measured. So this is the Helings and Downs. This is the energy spectrum over here. And for basically most of the talk, I'll just basically only talk about this energy spectrum, and we'll not really discuss the Helings and Downs correlation anymore. But this is what this claim detection relies on, is the significance of this correlation. So these efforts are international. So there are a variety of PTA collaborations that together announced evidence for gravitational waves. In North America, there's Nanograv. Europe and Indian PTA combined their data sets to produce their measurements. There's Parks in Australia and the Chinese PTA as well. So there's an international effort to do this. So what I'll spend most of this talk discussing is, we've made this measurement. what can we get out of it? What are we learning from this? So first, I'll talk a little bit about how there's a simple upper limit for the maximum gravitational wave background that you should be able to produce, given our observations of supermassive black holes that have informed our understanding of electromagnetic observations that have informed our understanding of supermassive black holes so far. And then I'll discuss a little bit what a more detailed modeling of the statistical distribution of the gravitational wave background, given Poisson fluctuations in the number of sources. What doing this can teach us about what we're seeing in this gravitational wave signal. And so all this work was done in collaboration with Matthias Solderaga and with Elliot Pottert in these two papers. Right, so as I've already sort of mentioned, pulsar timing arrays sit in this bottom frequency band. So this is LIGO, LISA, and PTAs are this like lower frequency, are in this lower frequency regime. The minimum frequency is roughly determined by it is inverse of the total observing time, whereas the maximum frequency is basically set by the cadence with which you go back and measure the period of the pulsars. So this is what sets the frequency band that PTAs can observe. And the typical sources that we expect, and in fact, the only actual significant astrophysical source in this regime are supermassive black holes, inspiralling supermassive black holes. And just to give a sense of scale for the physical picture that we're discussing, so we're observing pulsars in our galaxy, so roughly kiloparsecs away. The typical sources are these supermassive black holes at like cosmological distances, so typically hundreds of megaparsecs to gigaparsecs away. And the gravitational wave frequency that they emit in is to be computed by just using Kepler's law. The gravitational wave frequency is twice the orbital frequency. So if you just plug this in Kepler's law, you can basically see that a like 10 to the 9 solar mass black hole at some subparsec separation will be producing sort of 10 of nano-hertz frequencies. And this sort of captures the typical object that should be emitting in the PTA band, and that will be relevant to the rest of the discussion. So the expected signal are supermassive black holes. What else do we know about supermassive black holes? So we know in a lot of detail about supermassive black holes that live in sort of nearby galaxies. You can, after the Hubble Space Telescope, for example, there was enough resolution to really study, to resolve individual galaxies and infer the mass of the central object, of the object at the center of galaxies. And you can, some of the best estimates of masses of black holes come from this like kinematics of the centers of nearby galaxies.
Do you mind telling us what the axes are of your plots?
This one?
I don't have a good enough eyesight.
Okay, yeah, I'm getting there, yeah. So this is basically showing the black hole mass and the properties of galaxies. And so this is
the properties.
Yeah, so this is so okay. So there are with these studies, there were correlations between properties of the host galaxy, which is shown in the x-axis, and the masses of the black holes were found. And this, so there are these. So this is showing this relation between property of the host galaxy and black hole mass. This in particular, this is the velocity dispersion. People have looked at other things, but that are basically related to the mass of the host galaxy. And so this is suggests some kind of coevolution between galaxies and black holes, and became something of interest in kind of galaxy evolution. Beyond local galaxies, and as importantly, this can only be done for relatively nearby galaxies. So the total sample here is around like 150 galaxies for which you can actually get these well-resolved spectra of galaxies. So beyond our local universe, we rely on supermassive black holes that are in the process of accreting. So quasars are thought to be powered by accretion onto a central supermassive black hole. And a kind of simple way to think about what quasars are telling you about them is basically through an energy conservation argument, which is usually called the Sultan argument. But the basic idea is just that if you have some blob of gas around the black hole, and some part of it is falling into the black hole and increasing its mass, you can say that some fraction of that will be radiated away, producing the total luminosity of quasars that we observe. And this fraction is set by some parameter. And what this means is that if you measure the luminosity function, so the number of quasars per luminosity over all redshifts, this is telling you directly what the mass density accreted onto black holes was given these parameters. So these observations of quasars are basically telling you about the mass density in black holes by some energy conservation argument. And then from gravitational definitions, of course, what you're seeing are black holes that are in the process of merging. So the kind of standard lore about how this proceeds is basically that, every galaxy that we see appears to have a black hole at the center. Galaxies are known to merge, so therefore the central supermassive black holes may also merge. How this exactly happens is sort of unknown, a lot of question marks here. This is called final parsec problem. But we observe supermassive black holes in this PTA range in these sort of sub-parsec separations. So somehow nature takes care of this. And we observe them in this regime where they're expected to be just dominated by gravitational wave emission. So unlike what you see in like LIGO or LISA, for example, where you expect to catch the actual merger and ring down and so forth of the black hole, and in PTAs, you expect to be seeing them very early on, where your waveform is basically sinusoidal, and it's very simple to describe. It's basically Newtonian. And where each supermassive black hole is basically contributing at a given frequency. So just and it's at a single frequency. So coming back to what you can observe with pulsar timing arrays, as I mentioned before, the amplitude of your correlation of the variance essentially of your arrival time of pulses is going to tell you what the energy density per frequency is. And the way you can describe this is basically as an integral over all of your merging binaries times the energy spectrum that they produce. Every single binary is going to be evolving, and in the PTA range only due to gravitational wave emission. So you can predict what this energy spectrum looks like exactly, because this is so simple. And by basically saying that essentially the change in your orbital energy is equal to the power radiated in gravitational waves, this completely sets what your energy spectrum looks like. And you can show that your characteristic strain is just this power law that goes as frequency to the -2/3. So there's a very strong prediction for what this spectrum should look like, just given this like sort of simple physical picture of the sources that are being emitted, that are emitting your signal. So the main unknown is really what the amplitude of this signal should be, which will shift this. You can have deviations from the standard power law, and we'll talk about this effect from discrete sources in the second half. But for now, the main uncertainty here is just the amplitude of your gravitational wave signal. So, okay, how can we model this? Maybe one way that you might think of doing this is shown here on the left. It's basically to attach your black holes to something we know how to describe pretty well, say dark matter halos. We know how to describe the merger rate of halos well, and you want to make this prediction by assigning a galaxy and then assigning a black hole to that galaxy. And you'll have to do this as a function of redshift and maybe assume some kind of time delay between your galaxy merging and your black holes merging. And a lot of these things we don't really know, even at redshift 0. And so for you, I think you can quickly see how making this prediction, you quickly introduce a lot of uncertainties in predicting this overall amplitude, just given how much we don't know about these astrophysical processes. So a kind of clever way to do this, that was pointed out by Finney in 2001, is to realize that all of the supermassive black holes that we can observe at redshift 0 are potential remnants of mergers that happened in the past. So if I know just the single supermassive black holes today, what their abundances are, I can suppose, for example, that they merged once before in the history of the universe. Then the number of single black holes today will just be equal to the number of binaries as a function of total mass at some redshift in the past, where I still need to specify what this redshift distribution is. But this basically allows me to connect this number of black holes today that we can infer directly from observations to what the amplitude of the gravitational wave background should be.
Are you gonna tell us more about I mean, there's a lot that's not specified in that model.
Like what?
Well, like the number of previous mergers, the redshift distribution of the mergers.
Yes, we'll talk
Okay,
about,
well,
yeah.
okay, you'll tell us about this.
Yeah.
Okay.
So for now, I'm just assuming one merger. And I can rewrite this expression for the strain amplitude just as a function of this single supermassive black hole mass function. And where I've now averaged over the redshift distribution, and you just have a weighing by 1 plus e to the minus 1/3, and the mass ratio, so the symmetric mass ratio. And if you want to take an upper limit, I think this expression makes this very clear what your astrophysical model can do for you. You can take your amplitude from 0 up to some maximum value where you take redshift to 0 and mass ratio to 1/4, and that's the maximum amplitude that you could possibly produce from one merger, given all of the black holes that we see today. So I'll get to multiple mergers, I think, in a couple of slides. But basically, you can then take these scaling relations that I mentioned before, which basically tell you what the probability of having of a galaxy with some property, whatever property you want to use, X, to have a black hole of a mass M. And then you can look at a galaxy catalog that has the number of galaxies per this property, and you can just combine these things to produce an estimate of the black hole mass function and just plug that in here. So,
I just want to make sure I understand.
yeah.
The point here is that because this eta scaling, it's unhelpful for producing gravitational waves to have many previous mergers. The maximum is just to have one.
It's more about the mass. So I'll answer this question exactly in like 2
Okay,
slides.
great.
So just sorry. Yeah. So I can do this. I can take different catalogs and different scaling relations. And the mass function that I produce are shown here. So each of these lines are a different reference in the literature measuring these relations between black hole mass and property of the galaxy, and then different galaxy velocity dispersion functions, stellar mass functions, and so forth. And this gives me this range of predictions. And I can then estimate what the characteristic strain is. So these are these points over here. Each of these corresponds to one of these mass functions. And these are the values that were measured by pulsar timing arrays. And this distance between these two sets of measurements are kind of the point here. So the fact that this is close to an upper limit, and the measured value is slightly above this is curious. And it's what we pointed out in this work over here. Okay. So I guess one sort of obvious way to make more gravitational waves from the same resulting black hole population is to just have them merge multiple times. And one thing that you can show is that you actually get kind of diminishing returns because the masses of the black holes are smaller, right? So for example, in the simple limit where you just have equal mass mergers, at each previous layer here, you're basically saying that you have twice as many black holes, where n here is the layer, that were half of the mass. And because of this scaling with mass to the 5/3, you get a very quickly diminishing contribution to your background from multiple mergers. And you can take the limit when this goes to infinity, and basically the difference between black holes merging once and black holes merging an infinite number of times is 60%. And so you can at most get 60% higher background by just having them merge multiple times. And this is assuming infinite and instantaneous mergers. If you have some like delay between mergers, this will only further reduce the contributions that you get.
It reduces it because they're high redshift.
Uh,
Does it produce it?
So here I'm not changing, I'm actually not so for this limit, I'm not changing the redshift distribution at all. I'm just saying if they merge an infinite number of times instantaneously right now at redshift 0, this would be the maximum contribution that we would get, and you would get to this gray point over here. So what's changing here is just from the masses becoming smaller.
Sure, but the delay, but you said the delay would make it worse.
Yeah, so if I add a time delay between each of these, so here I am changing the redshift distribution. So for the first merger, I'm assuming some distribution, and then I just assume some fixed time delay and recompute the redshift distributions from the past mergers. But the point is that you just plateau earlier, basically, because you can only fit so many mergers within the age of the universe, and you don't get as large as 60%.
Oh, I see.
But so this point over here, I mean, you wouldn't call this statistically inconsistent with the nanograv result, but you did kind of have to take this absurd upper limit for you to get here.
You just explain it, I just didn't assimilate it, why it's m to the 5/3.
This just comes from the gravitational wave signal.
Well, I understand that,
Yeah.
but can you explain so I can understand the 5/3, or is it hard to understand?
Well, it comes just from computing. So basically you're saying that you have a.
No, I understand, never mind,
No,
it's, the answer is that it's not easy. I
Well,
thought
it
maybe
just
there
comes
was
from
a
the
simple
computing.
statement.
Yeah, I'm just thinking if there's a simple
Sure,
statement, but it
never
just
mind,
comes from like the
never mind.
quadruple
I got
form
the
it goes
answer.
from,
Yeah,
spiraling.
it's just the number,
Right.
it's the way it works,
Yeah.
okay, never mind, fine, it was just forget.
All right. Okay, so because you did have to take this, I mean, you did have to take this kind of absurd upper limit to get to something even at the like bottom of your uncertainties. We decided to explore a little bit more on how we could be misestimating, for example, the mass function. Like how much would you need to change your prediction for the mass function if you wanted to achieve the values that PTAs measure? So kind of a useful thing to keep in mind is just that the gravitational wave signal is scales as mass to the 5/3. And this kernel, so your signal is basically this mass to the 5/3 integrated over your mass function. And this peaks very strongly at pretty high masses. So you're basically just dominated by some characteristic mass that will pretty much determine your gravitational wave signal. And these masses are higher, for example, than the mass density, which dominates the mass density. But this also means that this really narrows what you need to change, basically, in your prediction. And so as a point of comparison, we add this black hole mass density, which is typically what you constrain from quasar observations, like I mentioned before. And we looked at varying a few parameters that are relevant for this prediction. So the basic conclusion is that you want to change the sort of high mass regime of your mass function. That's what you would need to be misestimating if you were to produce the appropriate, something consistent with the PTA observations. So this is changing the kind of Schechter function turnover in your mass function, and this is changing the scatter. So this is the scatter between your galaxy property and your black hole mass. So this scatter over here. And the bottom line is that if you want to change these parameters such that you match both the gravitational wave signal and the mass density that people commonly infer today, you need to change this. You need to change your prediction such that most of your the signal from gravitational waves is mostly attributed to these contours over here. So these contours are showing where 50 and 90% of your gravitational wave emission comes from in the space of your galaxy property and mass, where you basically have not seen objects living today.
Yeah, so rho BH, maybe you said this, but it assumes an epsilon R. And what is the nature of that
Yeah, so
assumption?
that is it's just an assumed value. Like you could change that and have a different black hole mass density. The goal of this was just to not try to rock the boat too much,
Right, but
and just keep that fixed. But it's true that it's
it
not
fixed at what?
like 0.1.
Right, so you can't
You can
make it that much higher without.
Yeah, exactly. But yeah, so by changing the parameters of your model, you're basically inferring, you're basically claiming that your gravitational wave signal is being produced by objects that have not been seen before, in these ranges over here.
What's the plot on the left? What is it? What are the two curves?
Yeah, so this is showing the curves of constant black hole mass density prediction and constant characteristic strain prediction. So if you live on these lines, you produce the same observed value of these two parameters. And so if you want them to be fixed to the current values, you need to look for the intersections of these curves, which are these sets of parameters x1 and x2 here. And these sets of parameters correspond to these contours. So these are the parameter values such that strain and mass density are constant and lead to gravitational waves being produced by these types of objects. Maybe more complicated than it needed to be, but so the main conclusion is that if you want to keep consistency with the mass density, you just need to change the high mass end of your black hole mass function prediction, which entails shifting your peak mass from this value of a few times 10 to the 9 that I had shown before to basically an order of magnitude higher. And if you can change the abundance, the mass density, or just the total number of black holes, you would be requiring about 4 to 10 more black holes than currently estimated.
So, but the discrepancy you show is like a factor of 2.
In the strain.
In the strain.
But the black hole, the number is proportional to the strain squared. So it's.
Because it goes as the number to the square root or something.
Yeah, so
And
strain squared is, the integral over the mass function.
But doesn't it also go as the mass to the 5/3? Or so why does the mass have to change by a factor of 10?
So it's either this or this.
Right,
So if you
no,
were
but
boosted-
but a factor of 10 increase in M doesn't give you a factor of 10 to the 5/3.
But its abundance is lower, right? So
Oh, but
it's,
the abundance is
yeah.
lower, I see,
So,
okay,
yeah.
got it, thank you.
Okay, so I'm gonna slightly switch gears now. Are there?
So
Any other
you're thinking like for simplified 2-parameter model, where abundance and typical mass. And there's, I don't know if I think in your paper you had this plot, maybe we'll show it.
Yeah. It's from this part, yeah.
Okay, perfect.
Yeah. Any other questions before I switch topics a little bit?
Yes, make sure I understand. So for the larger map, so that could. To square it with observations, could a possible source of that be that lower mass black holes are somehow easier to observe? Like, let's say they're less likely to be quiescent than the larger ones? Is that what's needed?
So I guess one is that your lower mass, the observational selection kind of goes the opposite way because the more massive black holes live in the brightest, most massive galaxies. So those are the easiest ones to detect. And then the other problem with assigning it to low mass black holes that we say we don't observe them very well and their abundance is higher than we're predicting. You just need, because of the mass of the 5/3 scaling, you just need a much larger factor. Like you need to be missing a lot more. Yeah. Okay, so now I'll talk a little bit about what else we can learn from the sort of shape of the spectrum. So far I've been talking about this average prediction, which corresponds to this power law shown in dashed here. But PTAs are indeed sensitive to the kind of full frequency spectrum, which is shown over here. So you do have some information about the strain at different frequency bands. And if your gravitational wave background is produced by discrete sources, there are kind of two main effects that you expect to see in your spectrum. One is our frequency to frequency fluctuations. So at each frequency you'll have, because they're, each frequency band is emitting, you just have some number of sources contributing to each frequency band. Fluctuations in the number of sources will just lead to fluctuations in the spectrum. And then the other effect that is maybe not so obvious as to why, but we'll get there, is that there's a drop off in this median. So the mean is always given by this power law, but your median kind of falls off a little bit. So these are the two main effects that you could maybe see in your spectrum that would tell you something about this number of sources that is contributing.
Could you explain what the black wiggly line in the left plot is?
So the black wiggly line is just one realization. So it's, say you have some distribution here, the mean is the dashed, this wiggly line is one realization.
Is it some model that they?
Yeah, it's one realization of one model. Yeah. But the point here is that, for example, if some frequency band you happen to live in a universe where you have one brighter source, then you would see this as a peak in your spectrum.
What did you say the red dashed curve was?
This is just highlighting this fall off in the mean, but it's not. I put that there. It's not in part of the.
In the median.
Yes.
Red dash is the median and the black dash is the median. So they don't actually match.
Yeah.
It's long option.
Yeah. So ideally, if you want to have a model and compare it to your observations, you would want to predict what this distribution is so that you can compare it with the data and tell something about the typical number of sources that are contributing at each frequency band. So this is what we did in this work. Basically, at each frequency that you observe here in the PTA, you can describe this as the sum of the contribution from each source emitting at that frequency. And what you want to do is describe the probability distribution of this sum. One useful thing to do is to write this in terms of this sort of luminosity function of gravitational waves. So instead of working in terms of the mass, the redshift, the mass ratio, you can just write this as the number of sources per gravitational wave amplitude. And for example, your mean will be equal to the integral of this quantity, the mean number of sources, the mean of your background will be the integral over this times the strain, and so forth. And some of these examples are shown here. They vary with frequency in a deterministic way. And this sort of luminosity function of gravitational waves basically completely characterizes the properties of your gravitational wave spectrum. And the shape of this luminosity function, this is shown basically here, the strain amplitude squared times your luminosity function. The shape basically follows from the shape of your mass distribution. Similarly as to how the mass distribution was peaked at a characteristic mass, this is going to be peaked at some characteristic strain amplitude. And one very useful quantity to think about is this characteristic number of sources, which is the total background, so the integral over each one of these curves, divided by this peak value. And so basically, if all of your background were produced by sources of your most important strain, how many would you need? This is this characteristic number of sources. And you can see that this one is pretty model dependent, and two, how precisely it is model dependent, and that it scales very strongly with frequency. So if you were curious about, when this starts to happen in your spectrum, like it might seem like a coincidence that you would just start to see these fluctuations kind of in this middle of your PTA band. This is basically because it is such a strong function of frequency. The dynamical range and number of sources is very large. So if your PTA captures like a decade in frequency, the typical number of sources varies by like 4 orders of magnitude. And if you want to call the point where these effects start to become important, as say where n is 1 or so, it's likely that you will see this happen within your PTA band just because your dynamical range is so large. But this will be a function of your astrophysical model. So, I mean, we compute the distribution of these characteristic strains. So you're basically describing the probability distribution of a quantity that is the sum of random variables that are each distributed according to this luminosity function, right? So the distribution of a single source is just proportional to this luminosity function that I was describing so far. And you can show that this is given by, so the number of sources. So this probability is basically the probability of having ns sources given some mean value, and that these ns sources combine to produce a total background ht squared. This is just a Poisson distribution, and this is given by ns convolutions of your single probability, and then summed over all possible number of sources. And this becomes very simple in Fourier space, and there's actually a long literature of doing this in various fields. This comes from like early radio astronomy, but has been adopted in various fields, including inline intensity mapping, for example. This is used. But so you can now compute analytically what these distributions of your strains look like. The kind of state of the art in the literature is just to Monte Carlo these distributions, which are shown in these histograms, but the results of the full calculation are these like solid lines here for the various models shown on the left. So there's an additional approximation that one can do. So one sort of clever thing to do is to rescale your strain by this peak value that I had mentioned before. And this turns out to absorb most of the parameter dependence. So if I write my luminosity function in terms of this rescaled parameter, you can show that this is basically given by your characteristic number of sources times this function mu. And this function mu is pretty close to universal. It's not perfectly universal, but here you can see various, so this is showing the mass function of black holes. This is showing the redshift distribution. This is showing the mass ratio distribution, and for various model parameters. And then here, these are the mu's, which are pretty similar. So this is what this basically means is that you just need to specify two values, the characteristic number of sources, and say the mean. And this completely determines what your distribution should look like. So this is the shape of the distribution, but now in terms of these rescaled parameters and with the mean shifted to correspond to this dashed line. And this is the shape of the distributions that you get for different values of characteristic number of sources. So at higher frequencies, you typically have a smaller number of sources. This distribution has a median that is much lower than its mean, which kind of explains this drop off that I had shown before. And you can now predict all of these with just these two parameters. They depend on frequency, of course, but they depend on frequency in a known way. So you really just have 2 degrees of freedom. And this really simplifies the kind of data analysis process. So on the right is the approach described by one of the standard nanograv analyses that involves computing like libraries of your astrophysical models, producing a library for this, sampling these to produce the distributions. And then because this is a very costly process, there's some Gaussian process to interpolate between your different PDFs. And then you get to compare this with the data versus in our case, we just have a 2-parameter family. You can literally do a grid and compute your PDFs analytically and just compare that to the data and constrain your models. And you know exactly what the degenerate combination of parameters is that you're measuring from the data.
So, but with these 2 parameters, could you actually capture everything like the delays, the phenomenological things?
The delays, yes. The one thing that we don't, I think the only thing here that we don't get is this turnover at low
Like-
frequencies. Yeah, we don't have anything for that, but you could just.
But they also don't need this like gigantic machinery for that.
Yeah.
Anyway.
Yeah,
The turnover at low frequencies is like when the evolution is being driven by things that are not gravitational waves. I see.
exactly.
Okay.
And
Uh,
when they do this complicated thing, do they find that in fact their predictions are 2-dimensional?
So they present a huge corner plot, and it's not clear there that you can reduce that to 2 dimensions.
But you're claiming that you can, so you
Yeah.
believe that if you visualize their results correctly, you would see that it was 2-dimensional.
Yes. Okay, so yeah, we take this, we compare it to the data, and we constrain these parameters. Here we plot this in terms of, I guess, more physically interpretable parameters, which are this peak mass that contributes to the gravitational wave background and the black hole mass density. So here, blue contour is what you require to fit the nanograv free spectrum. And this is using their publicly available data that over here. And then this red contour is what you predict using these scaling relations and the electromagnetic observations that I had discussed so far. The dashed lines are lines of constant characteristic strain. So if you had only measured the amplitude of the background, you would be completely degenerate along these dashed lines. These dotted lines are lines of constant characteristic number of sources. So the fact that there is a little bit of information about it, about this characteristic number of sources, is the reason why you get pushed in one direction versus being completely degenerate here. But you can see that you're mostly just detecting this overall amplitude, right? There's not much there. And the fact that there's no statistically significant evidence for some Poisson fluctuations in your signal, given how large the error bars are, means that you just get to place some kind of lower limit on the number of sources. So from the fact that you're not seeing significant evidence for these Poisson fluctuations, you basically constrain a lower limit here.
These contours extend to the left,
Yeah,
so I'm not sure you can answer
yeah.
this question, but what is like the meaning of these significance levels?
Oh, like here in this.
Yeah, I
this
mean,
difference?
you could answer the question for the red. It's not obvious to me you can answer it for the blue.
Yeah, so this is, right, so I mean, an inherent feature of this is that as you increase the number of sources, you always recover this kind of Gaussian limit where you're just indistinguishable from a perfectly homogeneous, like stochastic background. But there's always, if you increase the number of sources, that's something I mean, there's a regime where you can never distinguish the number of sources, right? Because it's just,
So it's
which
that
is
just
this upper
continues
corner.
up along that degeneracy
Yeah.
forever.
Yeah.
Okay.
Yeah. So here, I mean, the difference here between the blue, the middle of this blue, I guess if you follow this dashed line, and the red is the same exactly as the distance between those points that I had and the PTA measurement that I had before. It's just that here, the fact that you don't see any effects from Poisson fluctuations means that you're squished against your lower bound in your.
So
in your
you
plane.
prefer the first of your explanations, which is more.
Exactly, yeah. Yeah, so right, so the initially when we in that first paper, we thought that it would be easier for you to just be misestimating some small number of black holes at your high mass tail. So shifting this peak to the peak contribution to higher values. And that value would be 1 here and then 10.5 here, which is kind of not, is pretty outside of what you would infer. And yeah, so you are sort of in this larger number of fainter sources regime. Yeah, so there's already some information about the typical number of sources in the PTA data.
Is the idea that if you had like fewer than whatever one source, you would see the suppression of the
Yeah.
the median right away at the lowest frequency
Yeah.
panel graph?
Yeah, that is where, I mean, most of your sensitivity is just in the first 5 points.
Right. Yeah.
And also all of your constraining power is exactly from the fact that you don't see this drop off.
And what is the Q equal 1 to equals 1 figure? Is it somewhere that you could fix this?
Yeah, this is equivalent to that upper limit that I had shown before of the like infinite number of mergers. But here I just assume all equal mass mergers and a very short time delay. And then this contour is
Becomes
lowered.
more in agreement.
Yeah. So it's similar to that gray point that I had before in that plot. Yeah, so this is basically what I had to say. After we put out these papers, there was some interesting discussion in the community of like, what are possible explanations for this disagreement between your electromagnetically inferred amplitude and the PTA signal. And I think this is still up for debate. I'm happy to comment on some of the papers that came out sort of providing possible explanations for this. But I'll just leave it here that this is an ongoing discussion. And yeah, so this is more or less what I had to say. So you have this new observational window from pulsar timing arrays. There's a simple upper limit that one can predict from existing observations, and it seems to be a bit off from current measurements at least. And that there's already more information in the spectrum about the typical number of sources. Thanks.
Any last two questions for Gabby?
For me, it would be natural to say that the PTA is likely to overestimate the power. Just because, noise is noise and this is a subtraction of variances. Are people talking about that, or is the Hillings-Downs curve feeling that that's such a rigid model that is keeping them from?
The hope is that, yeah, the correlation would be a very stringent test of that. But that is, so this paper over here, on the right, here. This paper here is precisely looking at noise models and pulsars. So I mean, one possible source of this misinterpretation is that you've mismodeled the pulsar noise. That there's some feature in the noise that you have not
That's
captured.
not where I would look at all. I mean, the Hillings-Downs curve is in sum of a dipole and a monopole, I believe.
Actually, quadrupole and.
Sorry, quadrupole and
And but
quadrupole.
mostly quadrupole.
But it's also got a monopole because it's not.
No,
Well, it doesn't integrate to zero. It doesn't integrate to zero over the sphere, so it does have a monopole. You ever go to the Hillings-Downs curve?
No, it's like strictly starts at quadrupole. Like if
Can you
you
show me
compose
the
it,
curve?
yeah.
Let's just show me the curve and let's just see that, because I'd be interested to know if that's true, because this is kind of important from a noise perspective. Whether there's a monopole in it.
so just from the like quadrupolar nature of gravitational waves, you should not have, like, it should start at quadrupole.
I agree, that's why it's always slightly confused me why.
This is probably showing in terms of angles rather than cosine theta.
So you're saying that if I wrote that in terms of cos theta, it would integrate to zero?
Hard to believe. I agree.
But yeah, but this is not.
But it's, yeah.
That integrates to zero. So it must be somehow the fact that it's asymmetric. Up and down is offset by the fact that the minimum is not at 90 or something.
A lot
That's
of area
amazing.
there, 90.
It's amazing that has zero.
Sine theta.
It's amazing that has zero overlap with the monopole. But of course, your pulsars are not uniformly distributed on the sky.
Yeah.
So any actual estimate of this is not orthogonal to the monopole or to a dipole.
Yeah.
And you can
That
get
is
a dipole from the solar system or anything locally. right?
Yeah, yeah. I mean, that is part of the modeling, but it is true. That is part of it, yes.
But it's done in a strange way.
Yeah,
Like they're not, they're not marginalizing over monopole and the dipole, they're like comparing the evidence for them separately and,
yeah.
it's kind of strange. So I think if they marginalize over, probably the significance would become more.
Probably. But yeah, people, this is one avenue that people have looked at. It doesn't change the amplitude almost at all, taking these noise models into account. But that is something that has been looked into. But yeah,
And so your view is that the astrophysical part, like the local mass function of black holes is pretty robust.
so this is this is a paper getting at the black hole mass function measurement. And I think there's some confusion here about how this is being estimated that I'm working on right now. I think that no one has looked at the inference of the black hole masses themselves, like from the just the galaxy imaging and spectra and so forth, since these were measured by Hubble Space Telescope with you, like when this started to be done like a few years ago, like 10, 15 years ago. But most of the disagreements that exist come from just the mass functions as that you estimate for galaxy surveys. And there should not be that much variation. Like there's enough data to say something.
What? I kind of agree. What do I have to? How much do I have to worry about redshift evolution in this? Not at all, or do
Not
I
at
just
all.
need to know the redshift 0?
You just need to know the redshift 0, because it comes from just looking at the remnants, right? So
Right.
you just need to
Yeah.
estimate the mass function now.
And for some of your things, you were holding the mass density in black holes fixed. You had these things where you were changing the mass, the peak of the mass function, but holding the mass density in black
Yeah.
holes fixed. Why do you believe that's well measured?
That was so the argument comes mostly from the quasar luminosity function, but you could absolutely change that by just changing your radiative efficiency. It was mostly a what do you need to do to not change the current picture very much, but you could
So
absolutely.
if you dropped your radiative efficiency by a little bit, you could
Yeah.
increase that and you'd hit your targets.
Yes. But it's just that there's this trade-off that
Right.
you need to
Well,
address.
no, you have to raise your radiative efficiency. You
so
drop
it's,
it.
it's
You
drop
drop
it.
it.
Yeah, you drop
Oh,
it.
you
It's
drop
fewer
it.
photons per gram.
Yeah. So.
I mean, yeah, if it's 0, just all of your gas falls in and you don't radiate it.
Yeah,